Hello friends, welcome to the video lessons on electronic measuring instruments. In this class, I'll explain what are the conditions for stationary and flicker-free waveforms on CRO screen and what is a triggered sweep circuit and what is its importance. How do we get a stationary waveform in a CRO? How to get flicker-free waveforms in a CRO and about triggered sweep circuit. First of all, what is stationary waveform? Stationary waveform is the one or is a waveform which does not move or which appears to be stable on screen. To get a stationary wave on CRO screen, starting off the sweep should be in step with the input signal. That is, both the sweep signal and vertical input signal should be applied simultaneously. In step means both at the same time to the deflection plates, one to the vertical deflection plate, the other one to the horizontal deflection plate. Second important condition is the frequency of the input signal should be equal to the sweep signal frequency or should be an exact multiple of the sweep signal frequency. That is, in a time period of one sweep signal, at least one input signal should complete its full cycle, or it can be 2 cycles of the input signal, or it can be 3 cycles of the input signal, and so on. But the sweep signal should be a submultiple of the input signal frequency, or in other words, the input signal frequency should be an exact multiple of the sweep signal frequency. So what are the two conditions? First condition is both horizontal and vertical input signals should be applied simultaneously. And the second condition is the input signal frequency should be either equal to the sweep signal frequency or should be a exact multiple of the input signal frequency. What happens if this condition is not satisfied? If this condition is not satisfied, then what happens? That means on the CRO screen, full cycles of the input signal does not appear. Say for example, 1.5 cycle of the input signal is appearing and the remaining half of the second cycle starts from the beginning on the screen. Then what happens? One signal would be starting at 0 and it continues in the positive direction, and another signal would start at 0 and continue in the negative direction. So because it is a continuous stream of pulses, then we will observe the waveform either to be moving towards right or moving towards left. If the frequency is too high, then the pattern or the signal that is appearing on the screen continuously moves towards right from left. That is, left to right continuously it will be moving. We cannot visualize the exact waveform. Similarly, if the frequency is too low, then the signal appears to be moving continuously from right to left. Right to left. We cannot find a stable waveform. Here, how to control the unstable patterns? Actually, because of the mismatch between the sweep signal and the applied input signal frequencies, we get the unstable signal. So, in order to control these unstable patterns, there would be a provision on the CRO front panel, or in other words, in the circuitry of CRO, to adjust the frequency of the sweep signal. The sweep signal frequency can be adjusted by using a potentiometer. So now what happens by adjusting the potentiometer, the sweep frequency is made either equal or submultiple of the input signal frequency. Or in other words, the vertical input signal frequency is either equal to the sweep signal frequency or exact multiple of the sweep signal frequency. That is how we can adjust the sweep signal frequency. By adjusting that, we can get the stable waveform patterns on the CRO screen. Now, what does it mean by flickering? Flickering means on and off, on and off. So, whenever a waveform appears to be on the screen for a certain time and disappears for additional period of time, then once again appears, next immediately disappears, we say such signal to be flickering signal, and we cannot study such signals on the CRO screen, or we cannot study the characteristics of such signal on CRO screen, because the signal would not appear continuously. So, what should be the condition for flicker-free waveform? Now, here let us see. During the trace period of the sweep signal, electron beam deflects to a distance from left to right of the CRO screen. During the retrace period, it comes back to the initial position, that is from left to right. Now, just try to imagine, try to visualize a signal appearing on the screen moving from right to left during the trace period, and during the retrace period the sweep signal makes the luminous spot, that is the electron beam, to move from right to left. So when these two signals are superimposed, left to right one movement followed by right to left another movement, when these two signals are superimposed, we will find a flickering waveform on the screen. Why flickering? When two waveforms which are moving in opposite directions come across each other, they will nullify. they will nullify, and we will not find a waveform at that particular point. So the signal appears to be flickering, just shaky. In order to avoid this flickering, then we have to block the movement of the electron beam from right to left. So we have to make the retrace of the electron beam invisible. By doing this, what happens? The screen is blanked at the rate of the sweep frequency. When the screen is blanked during retrace period, then we can get a flicker-free waveform on CRO screen. So sweep frequency should be greater than 16 Hz. Why? First condition is the retrace signal should be blanked. Second condition is the frequency of sweep signal should be greater than 16 Hz, because the persistence of human eye, or the persistence time of human vision, is 1 by 16th of a second. That means when you see an image, even when the image is disappears, even when the image disappears in front of your eyes, the eye will retain its image till 1/16th of a second. So when the luminous spot appears for a duration of 1/16th of a second, then we can find a continuous and smooth waveform on CRO screen. That means if the sweep signal frequency is less than 16 Hz, then what is the time period? 1 by 16. When the time period is less than 1 by 16, then we will not find a continuous waveform on CR. We will find a flickering waveform. To prevent that, the frequency of the sweep signal should be either 16 Hz minimum, or it can be even greater than 16 Hz also. Generally, the supply frequency is 50 Hz for us in India. So we can use this frequency as sweep signal frequency. So the recommended sweep signal frequency is 50 Hz, because directly we can take the signal from supply mains and it can be converted into a sweep signal with 50 Hz. Now, what is a triggered sweep? Triggered sweep is a circuit used for blocking the retrace signal. That is one thing. And it is also used to produce trigger pulses whenever we need the trigger pulse. Otherwise, no trigger pulse can be, I mean, for the remaining period of time, there would be no trigger pulse on the CRO for sweeping the electron beam from left to right. Here you can see the block diagram of a triggered sweep circuit. As you can see, trigger selector switch here, it is given as one input to a comparator A, and the other input to the comparator is through a potentiometer, which provides a reference voltage to this comparator. By adjusting this trigger level, or by adjusting this potentiometer, we can get a reference voltage for this comparator. Now, depending upon the trigger selector, if it is in external position, we can get external signal as the trigger input. If it is connected in internal position, vertical amplifier output is taken as the input to the trigger circuit. If it is in the line position, as I told already, amplitude reduced AC mains signal is used as the input to the trigger circuit. The trigger selector connects the comparator to either the output of the vertical amplifier or to the external trigger or to the secondary of the low voltage transformer line. The reference level of the comparator is set by the trigger level. The comparator gives, that means this one, the trigger level. This is the one which is used to produce reference level to the comparator. The comparator gives out its output when the trigger input signal exceeds a particular value as set by the trigger level control. Here certain value is there, say some V1. If the voltage here exceeds V1, the output will change to one position. If this voltage is less than V1, the output would be in another position. A Schmitt trigger that follows the comparator generates negative trigger pulses to sweep generator each time the comparator output crosses the trigger level. That means whenever the vertical amplifier output here exceeds the trigger level, a pulse is generated here. That pulse is converted into a negative trigger pulse. Initially it would be high, and whenever a pulse is generated here, that would be converted into a high to low transition. A negative pulse is generated for every pulse output at the comparator. That means for every uh, time when the vertical amplifier output exceeds the trigger level. This triggers the sweep generator to start the new sweep. How? That we will see here. Here is the trigger input. That is a negative going trigger. Now, if you see the circuit here, it is a UJT relaxation oscillator, that is normal sweep generator circuit with additional circuitry connected to this. What are all the additional parts? One is the coupling capacitor here. Trigger input is connected to the base 2 of this UJT through this capacitor, and another one is a diode D here, and another potential divider network R3 and R4. Here what would be the potential at this point, that is VD? VD is equal to VBB by R3 plus R4 into R4, that is VD. So the cathode of the diode D is at a potential VD, and the anode of the diode D, it would be continuously, it would be an exponentially increasing voltage on the capacitor. When you turn on the power supply, let us assume that initially the voltage on the capacitor is 0 as such. So, with a time constant of RTCT, the voltage on the capacitor starts increasing. and the instantaneous voltage on the capacitor would be given by the expression VBB into 1 minus e power minus T by RT CT. And this is an exponentially changing capacitance voltage. When this voltage exceeds this voltage Vd, diode starts conducting. When this diode starts conducting, the capacitor voltage will be clipped to that voltage Vd. It cannot charge beyond that. Maximum it can charge to a voltage Vd. And here the values of R3 and R4 are chosen in such a way that this Vd is very much lesser than the peak voltage of UJT. What is peak voltage? Peak voltage is the voltage of UJT at which the emitter base junction starts conducting and UJT starts conducting and the resistance R1 decreases abruptly because of the surplus flow of charge carriers. When the number of charge carriers in this region increases, naturally the resistance decreases. So R1 resistance decreases, and as a result the voltage across emitter and base one also decreases. So anyhow, that is how the UJT will conduct and will turn on. Now, when the potential on voltage on capacitor CT is fixed to Vd, it cannot exceed till Vp. So this UJT does not conduct at all. So when UJT does not conduct, capacitor charges to a voltage Vd and remains constant there. Now, when a negative trigger pulse is applied here, then automatically the UJT starts conducting because the peak voltage temporarily would be reduced below the value of Vp. So when this UJT starts conducting, the capacitor discharges through this portion at a very faster rate, because when the UJT is conducting, R1 value would decrease rapidly to a very low value. So the capacitor discharges very quickly till what? Till the valley voltage of the capacitor, valley voltage of the UJT. Once the voltage on the capacitor falls to valley voltage, then UJT automatically turns off. And once again the transistor starts conducting, starts increasing, or the voltage on the capacitor starts increasing, or the capacitor starts charging towards voltage Vd. So what is happening here? Initially when you switch on the power supply, capacitor charges up to Vd and remains constant. Now when a trigger pulse is applied here, then voltage on capacitor decreases at a very faster rate to V valley, and after that UJT turns off and once again the capacitor charges to Vd, and after that it remains constant. So as you can see here, when trigger pulse is applied, the sweep starts with a retrace signal followed by a trace signal. So retrace signal comes first and trace signal comes next. So somehow if we can block this retrace time or retrace signal of the trigger input or the sweep input, then we can avoid flickering of the waveform on the CRO screen. So that is why A triggered sweep circuit will be helpful in producing flicker-free waveform. And also, if we want to measure only a particular portion of a signal, then only for that period the sweep is generated and the signal is analyzed only for that period. Because if it is a continuous sweep signal without this arrangement, then on the CRO screen, the portion of interest which we need to analyze will be swept off from left to right within no time. But that is not we are interested in. That is not what we are interested in. We are interested in to analyze that particular portion. So only for that portion we produce sweep so that the signal or a portion of the signal which is of interest or which needs to be analyzed only will be swept across from left to right of the CRO screen, and after that the sweep generator stops producing sweep signal. So as long as the persistence of vision is as long as the phosphorescence of the phosphor material used is greater than the persistence of vision of human eye, we can visualize the signal on the CRO and we can analyze the signal. Now the detailed description is given here. From the figure 3.38.7, that is this one, it can be observed that this is a modification of the UJT sweep generator. A voltage divider is formed by two resistors R3 and R4 applied across the power supply VBB. The values of R3 and R4 are so chosen that the voltage on the cathode of diode is less than the peak voltage of UJT. The timing circuit consists of RT and CT and is connected to the power supply VBB. UJT is connected as shown in circuit with R2 in base 2 and R1 in base 1 circuit. The diode is placed between the midpoint of R1C1 combination. For timing and potential divider formed by the R3 and R4. The diode is placed between the midpoint of R1C1 combination for timing and the potential divider formed by R3 and R4. When the supply is switched on, the capacitor starts charging through the resistor RT towards VBB till that point where the diode becomes forward biased and starts conducting. As the diode is conducting, the capacitor CT is clamped at a voltage VD, that is the voltage at the cathode of the capacitor, which is nothing but VBB by R3 plus R4 into R4. It cannot reach the voltage Vp required for conduction of UJT. If a negative voltage of sufficient amplitude is applied to base 2 of UJT, the peak voltage decreases momentarily and the UJT triggers or UJT turns on. Therefore, the capacitor discharges through the UJT till the minimum maintaining voltage, that is valley voltage, as shown in the waveform is reached. Once the capacitor voltage reaches the minimum level, UJT automatically turns off. So the capacitor once again charges towards VBB and it is clamped to VD. It cannot charge beyond VD. This process repeats as long as the supply voltage and the trigger pulses are present. The sweep waveform is as shown in figure. Yes, you can see here. When a trigger pulse is applied, the sweep signal starts with its retrace signal, followed by the sweep signal. Then once it reaches VD, it remains constant. When another trigger pulse is applied, starts with retrace, back to trace and then constant. So from here to here only the signal is applied to CRT and we can see only forward movement of the electron beam, no reverse movement of the electron beam. That is why we get flicker waveform. It must be noted that the trigger pulse initiates the retrace before the sweep could be generated. Hence, the part of the waveform corresponding to the retrace period would be lost. The delay line used in the vertical deflection section of the CRO will also make sure that the part of the waveform corresponding to the retrace period would be blocked. Now, just you see how syncing takes place. Need of sync pulse. Here, two cycles of signal waveform occur in same time interval as one cycle of the sweep signal. Two input signals and one sweep signal. Now, on the CRO screen, we will get full one input signal fully, half cycle of the second input signal fully, a portion of the negative half cycle on the CRO screen. Then this portion, then the next screen does not start from here. Here rather, this signal is blocked by the circuit and once again from here it will start. So next screen also appears the same. Third screen also appears the same. So we get a continuous waveform without any flickering. Additional syncing pulses. Now we have seen the triggered sweep circuit producing continuous triggering pulses. Now how it gets adjusted, how the sweep signal gets adjusted to the triggering pulses, you can see here. Initially, when a trigger pulse is applied, the capacitor would be in the process of charging and of course it discharges also. During the next trigger pulse also the capacitor is in the process of charging and then discharges. As the process goes on continuously, the moment that the trigger pulse is applied, the sweep starts with its retrace and then charges till VD, then it remains constant. And when another trigger pulse is applied at the same time, by that which the capacitor charges to VD, then another cycle of sweep starting with retrace first, then trace next. It goes on like this. So there is no possibility of flickering of waveform using this type of arrangement. To produce a stable display, sweep generator must run synchronously or in step with vertical signal source. Sync signal lowers the peak voltage of UJT. Every time when sync signal is applied, UJT peak voltage will temporarily is brought down and it is turned on. With UJT turned on, capacitor discharges at a very rapid rate to V value, and then after that UJT turns off and capacitor linearly charges to VD. Sync signal lowers the peak voltage of UJT and the run-up ramp prematurely, and ramp would be uh, generated prematurely. Sync pulses are superimposed on peak voltage of UJT, just like this as shown in figure. Now, what are the other advantages with the triggered sweep circuit? One is it produces flicker-free waveform. Apart from that, the signals of variable frequency and amplitude can be displayed like music signal, voice signal, and signals of very short duration and narrow pulses. So all these types of signals can be analyzed or can be visualized on a CRO screen using triggered sweep circuit. So this is all about how to get stationary waveforms on CRO, how to get flicker-free waveforms on CRO, and how to produce uh, triggered pulses using a triggered sweep circuit. That is all this for today. Thank you.